Where could something so massive remain hidden? How could a planet larger than Earth escape detection despite our advanced telescopes and sky surveys? The answer lies in the vast scale of the outer solar system. Planet Nine's potential hiding place encompasses an almost unimaginably huge region.
The cosmic hiding place. Where in our vast solar system could something so massive remain unseen? The answer lies in the extraordinary scale of space beyond Neptune. The visible solar system that appears in textbook diagrams, the 8 planets from Mercury to Neptune, represents only a tiny fraction of the Sun's gravitational domain. Beyond Neptune stretches a region so vast and dimly lit that even large objects can hide effectively from our telescopes. Planet Nine's predicted orbit places it hundreds of times farther from the Sun than Earth. While Earth orbits at a comfortable 93 million miles from the Sun, 1 astronomical unit or AU, and Neptune circles at about $30 Planet Nine would orbit at an average distance between 400 and 800 Australian dollars. At 700 Australian dollars, Planet Nine would be approximately 65 billion miles from the Sun, a distance so enormous that light itself, traveling at 186,000 miles per second, would take over 4 days to reach the planet from the Sun. To grasp this immense scale, consider that the entire orbit of Neptune, which defines what most people consider the edge of the planetary solar system, would appear as a small circle when viewed against Planet Nine's vast orbital path. If Neptune's orbit were represented by a large pizza, Planet Nine's orbit would extend well beyond the boundaries of an entire football field. The orbital calculations for Planet Nine reveal its extreme distance and several other distinguishing characteristics. The mathematical models suggest an orbit with significant eccentricity, meaning it's highly elliptical rather than nearly circular like most planets. While Earth's orbit is almost a perfect circle, Planet Nine would follow an elongated path that takes it from about 200 Australian dollars at its closest approach to the Sun, perihelion, out to approximately 1,200 Australian dollars at its most distant point, aphelion. This elongated orbit creates substantial detection challenges. The planet spends most of its time at the farthest parts of its orbit, where it moves slower and is hardest to see. At these distances, Planet Nine would be approximately 1,000 times fainter than Pluto as seen from Earth, reflecting minimal sunlight back toward us. Adding to the concealment, Planet Nine's orbit is significantly tilted. The models suggest an inclination of about 30 degrees relative to the plane of the solar system. This means Planet Nine travels on a different plane than the other planets, requiring astronomers to search not just far from the Sun, but also above and below the main planetary plane. Together, these 3 orbital characteristics, extreme distance, high eccentricity, and significant tilt, create the perfect cosmic hiding place. Planet Nine exists in a region where the Sun appears merely as a bright star, providing minimal illumination. The little light that does reach Planet Nine must then travel all the way back to Earth before we can detect it, resulting in an extremely faint signal. The planet's motion further compounds the detection difficulty. At 700 Australian dollars, it would shift by only about 3 arc minutes per year, roughly 1/10 the diameter of the full moon. This glacial pace makes it difficult to distinguish from background stars, requiring observations spaced months or years apart. With an orbital period between 10,000 and 20,000 Earth years, Planet Nine completes less than 1/millionth of its orbit in a human lifetime. Over decades of observation, it would appear to move in almost a straight line rather than showing noticeable curvature in its path. These factors combine to create an astronomical needle in a haystack problem. The search area spans hundreds of square degrees of sky, equivalent to searching an area hundreds of times larger than the full moon. Within this enormous region, astronomers must detect a tiny point of light moving almost imperceptibly among thousands of background stars and galaxies. Planet Nine likely resides in what astronomers sometimes call the inner Oort cloud, or distant scattered disk, a transitional region between the Kuiper belt and the hypothesized Oort cloud. This frontier extends far beyond where most spacecraft have ventured. Even the Voyager probes, which have left the solar system after traveling for over 40 years, have only reached about 125 Australian dollars and 105 Australian dollars respectively, still much closer to the Sun than Planet 9's predicted orbit. The vastness of Planet 9's orbital domain, combined with its faintness and slow movement, creates the perfect hiding place for a substantial world. Despite being potentially larger than Earth, it remains hidden in the darkness of space, challenging our current observational capabilities. Finding such a distant, dim, slow-moving object presents immense technological challenges. The hunt for Planet 9 requires sophisticated detection methods and powerful telescopes capable of piercing the darkness of the outer solar system, technologies that are just now becoming available to astronomers in their quest to unveil this mysterious world. The hunt begins. What technology could possibly spot a world hiding in the darkest reaches of our solar system? Finding Planet 9 presents one of the greatest observational challenges in modern astronomy. Despite being potentially several times larger than Earth, this hypothetical planet remains hidden due to its extreme distance and the minimal sunlight it reflects back to Earth. Conventional telescopes face significant limitations when searching for Planet 9. At 400 to 800 astronomical units from the Sun, any reflected sunlight would be approximately 100 million times dimmer than Neptune, while its slow motion makes it difficult to distinguish from stationary stars and galaxies. Add to this the vast search area, hundreds of square degrees of sky to examine, and you have what amounts to an interstellar game of hide and seek, where the hider has chosen the darkest corner of our cosmic backyard. Could this elusive world be hiding in plain sight, already captured in our astronomical data, but not yet recognized? This question drives astronomers to develop specialized techniques for their hunt. One approach involves multi-year sky surveys that systematically photograph large areas of the night sky repeatedly over time. By comparing images taken months or years apart, astronomers can identify objects that have moved slightly, a signature characteristic of distant solar system objects rather than stars or galaxies. These surveys generate massive amounts of data requiring sophisticated computer algorithms to process. These algorithms detect extremely subtle position changes while filtering out instrument errors, cosmic rays, and other artifacts. Today's high-performance computing makes this possible, allowing astronomers to sift through terabytes of image data looking for that one moving pixel that might represent Planet 9. While visible light searches continue, infrared astronomy offers another promising avenue. Planet 9 retains internal heat from its formation and from the decay of radioactive elements in its core. This heat radiates as infrared energy that specialized telescopes can detect, making the planet appear brighter in infrared compared to its extremely faint visible light reflection. The Infrared Astronomy Satellite, IRIS, and the Japanese Aerospace Exploration Agency's Akari satellite have provided valuable data for this search. These space-based infrared telescopes performed all sky surveys that might have captured Planet 9, even though they weren't specifically looking for it at the time. A study led by astronomer Terry Long Fan of the National Tsinghua University in Taiwan demonstrates this approach's potential. Fan's team analyzed data from both IRIS and Akari, looking for objects that appeared in the IRIS database and showed movement when observed by Akari 23 years later. The perfect time separation for identifying slow-moving distant objects like Planet 9. The team searched for objects that moved between 42 and 69.6 arc minutes over that 23-year period, the expected motion range for a planet at Planet 9's predicted distance. This methodical approach filtered out millions of static objects, focusing only on potential candidates showing the right movement over time. Remarkably, Fan's team identified a single object as a strong Planet 9 candidate. This object appeared in one position in the IRIS image and was detected by Akari in a slightly different position 23 years later. The movement matched what would be expected from a distant planet orbiting the Sun. However, with only 2 data points, the team couldn't determine the object's full orbit to confirm its planetary nature. Meanwhile, some of the world's largest telescopes have joined the hunt. The Subaru telescope, an 8.2-meter optical infrared telescope on Mauna Kea in Hawaii, has conducted dedicated Planet 9 searches. Its large mirror and wide field of view make it particularly well suited for this search. The telescope's Hypersum Prime can capture an area of sky equivalent to 7 full moons in a single exposure, efficiently searching large areas where Planet 9 might be hiding. Other facilities contributing include the dark energy camera on the Victor M. Blanco telescope in Chile. This camera's extremely wide field of view makes it excellent for survey work and follow-up observations of potential Planet 9 candidates. The technology used represents astronomical observations cutting edge. Modern telescope detectors can register individual photons, making them thousands of times more sensitive than photographic plates used just decades ago. Computer systems can analyze billions of pixels of image data, identifying moving objects that human eyes might never notice. Despite these impressive technological capabilities, the search remains challenging. Planet 9's extreme distance, faintness, and slow motion test the limits of even our most advanced instruments. However, astronomers remain optimistic. Historical precedent suggests that mathematical predictions of unseen planets can lead to successful discoveries, just as calculations by Adams and Leverrier led to Neptune's discovery in 1846. The most promising developments lie in the near future, with next-generation instruments set to begin operations in coming years, potentially bringing Planet 9 from mathematical hypothesis to confirmed discovery.